I think
Afternoon, everybody. So it's my pleasure to is graduated from University degli Studi La Sapienza at Rome as a Bachelor of Mathematics, and afterwards he is doing a master of Mathematics at the same University degli Studi La Sapienza at Rome, and afterwards he go to the Tokyo Institute of Technology, and his research is in theoretical physics. And afterwards, he did a PhD in theoretical physics at Tokyo as well, and is
Hmm.
become a assistant professor at Tokyo Institute of Technology, and then become the a research fellow in the university. He's a assistant professor in National University of Singapore, and so he is going to give us a talk today. And his talk title is Multiplicative Average Transitions and Applications. Okay, let's welcome him to give us the talk.
Thanks a lot. Thanks a lot for the introduction. I have to say one thing. So during the introduction of Curioli, there were some breaks. I'm not sure if the problem is my connection or is his connection. So in case there is a break when I speak, of course, yeah, you please ask me to repeat because.
So I can hear you very well. So I think you're okay
Okay.
now. Thank you.
Okay, very good. Thank you. So thanks a lot for the invitation. It's nice to meet you, meet you, and I met Valentin a few weeks ago when he visited Singapore. Okay, then let's start. Let me enter into presentation mode. I guess everybody can see the screen in full presentation mode. Okay, so let's start this word. So multiplicative averages of Plancherel random partitions. So everything will be every word in this title. I aim to explain in detail all of the words. But before doing that, let me say that this is a joint work with collaborators, Matteo Cafasso from Angers and Giulio Ruzza, which is assistant professor in Lisbon. Okay, so the title talks about the Plancherel measure. So let's discuss what is the Plancherel measure. So on the right, you see a partition. A partition is a list of numbers. We can list the length of these diagonal components here, for example, and depict a partition in this way. For example, in this case, a partition is a sequence of rows. The first row is as length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So for example, this is a partition whose first row is 11, whose second row is 1, 2, 3, 4, 5, 6, 7, 8, and so on. So the Plancherel measure is a way of producing a random partition, of attributing a probability measure to each of these partitions. We assume that the total number of boxes that you see on the screen is a fixed number, n, and we give to a partition lambda a probability which is equal to n factorial divided by a function of the partition squared. So this function is called the hook product, and we square this hook product. And this hook product is defined as follows. So to each of these boxes, which we call S, we associate a function, which is called the hook of the box S. And the hook of the box is nothing but the number of these dark orange cells. For example, this particular box here has a hook content equal to 12, because if I put myself on this corner and I look north west, I count 1, 2, 3, 4, 5. If I look northeast, I count 1, 2, 3, 4, 5, and 6. And then I also have to, so I have 5 plus 6 plus the location plus the box itself. So I count 12 boxes. And if I count, so if I compute the hook content for each one of these boxes and I take the product, this is the result of this function hook of lambda. So the fact that the right-hand side is positive is completely elementary, but the fact that these in fact define a probability distribution, meaning that if I take the summation over all of the possible partitions with n boxes, the fact that this right-hand side sums to 1 is quite non-trivial, but it's in fact a standard result in the representation theory of the symmetric group. So why is so this Plancherel measure? In fact, it's one of the most famous, if not the most famous, measures or probability measures on random partitions, and it has quite a long history. It was first introduced, although I don't think it was called a Plancherel measure, but it was first introduced, that I know, by Schoenstedt in 1961. As a way of studying the problem of the longest increasing subsequence. So we will see something, some example of what a longest increasing subsequence is on the next slide, but you imagine that you have a permutation of n elements, and this permutation, you take this permutation uniformly at random out of all of the n factorial permutation of n numbers, and you check on this permutation the longest increasing possible subsequence that you can find. And this is going to be a random number, which Schoenstedt understood to have the same length, the same law in probability of the first row of a Plancherel random partition. So this, the problem rephrased by Schoenstedt in this way, was later analyzed famously by Logan, Shep, Verchik, and Kerov, and later by the names that you see, Bike and Johansson, for example, they have a famous result, but also many other people. So I think that many mathematicians have contributed to our current knowledge of the Plancherel measure. What we study in this, what we talk about in this talk is a slight variant of the Plancherel measure, where the number n. So before we had an n fixed, and we maybe think of n as a large number. But in this case, instead of having a fixed number n, we have a random number n, which is sampled as a Poisson distribution with a parameter, a positive parameter, which I denoted by t squared. So this procedure of randomizing the number of boxes in the partition modifies the Plancherel measure in a minimal way, and the result is what you see in the screen. This Plancherel measure is slightly more manageable mathematically, but and it was studied in including in the paper by Teft and Johansson, but later on by Okunkov, Borodin, and other mathematicians. So let me just give a visual example of why such a measure is a popular and object that has been studied for a while. So take this square, which is a t by t square, and on this square you sample a Poisson point process, namely with intensity 1. Namely, you put points at random with intensity 1 independently everywhere. Then we can let now t grow to infinity, and we check the longest possible path. I mean, not the path from the bottom left corner to the top right corner, which goes up and to the right, and that connects the maximum number of these points. So this is a visual way. This is a way of visualizing the longest increasing subsequence in a Poisson inside a Poisson point process in a large box. So this it had been the original object, the original motivation of Schoenstedt to introduce this measure, to find how large is the number of points that you can collect with an upright path. or equivalently to find the average of the longest increasing subsequence, and a result, a result by Verschiker Logran shape is that this length is very close to twice the size of the box, and Bike-Dykes and Johansson in their famous theorem also characterized the lower order correction. So, but for the purpose of this talk, it suffices to recall that on average, a Plancherel random partition, which we see here, has a first row, which is approximately twice the parameter t, which appears in the definition. Okay, so this another proof of the fact that this is a famous object in probability is the fact that now this video was an excerpt from a YouTube channel, which is a very nice YouTube channel called the Spectral Collective, where they discuss about this measure. So let me recall some more history. So the Poissonized Plancherel measure exhibits what is called a limit shape phenomenon. This was characterized again in the 77 in a work by Logan Shep and Berchik and Kerov. These are independent work which found more or less the same result, which says that if instead of considering the partition, I consider the associated Maya diagram, which is the point configuration that you see by projecting downward slanted segments into a particle and upward slanted segments into a hole. So this creates a bijection between a point configuration, which is these blue points, and a partition. And this point configuration has the property that is fully packed to the left and empty eventually to the right. So they found that if I consider the empirical measure of the Maya diagram of this point configuration, then this empirical measure, if I take t very large, approaches a limit shape which can be described explicitly, and in fact its formula is so simple that it fits not even a line, it fits a third of a line. And this is what is called the arc cosine law, and it's written in this form. So the empirical measure, which is defined here, so probably maybe not many people know. So the empirical measure tells you how many points are there in a macroscopic segment of sides of order t, for example, t between A and B. The number of points falling between in these segments can be computed as the integral of a certain function, which approaches a deterministic function, the deterministic function written here. So you have to imagine that we are sampling here a Plancherel measure after a rescaling all the dimensions by t, and this is what we should observe by looking at this random partition from afar. So we can also notice that the first row so the support of the empirical measure which is also the length of the first row, is as the support to the right at 2, which is in correspondence to the fact that of the result stated in the previous slide, that the first row of the partition has more or less length 2t. Actually, in the paper by Logan and Shep, they achieved more, and they in fact determined also limit shapes under constraints. So, for example, assuming that we are sampling a Poissonized Plancherel, they did not consider the Poissonized Plancherel measure, but assuming that we are considering a Plancherel measure, and we force the first row to be below. Of course, the first row would really like to have length 2t, but assuming that we force it to have length 1.5t. So does such a random partition under this additional constraint have a limit shape, and can this limit shape be described explicitly? Well, Logan and Shep found that yes, it can be done, and in their paper they also presented this plot, which I report here, and the plot tells you what the limit shape is supposed to look like when you impose constraints. Of course, the difference between the plot given here in orange and this plot here is simply a rotation of 45 degrees to the left, and you can see that the bold, the solid line corresponds to this picture here, whereas the other dotted line correspond to limit shape under further constraints. Okay, so this is all my history on the Plancherel measure. There would be much more, but I stop here. Of course, the result by Logan and Shep can also be used, since we have the large deviation type results for the full shape. One can extract also informations about only the first row by tracing over all of the possible by essentially using the result. And this result was used later, 20 years later, by Sepalainen and Zaitoni to establish a large deviation principle for the distribution of lambda 1, which is this object shown in the video before. Okay, so the content of this talk is a study of a very simple functional of the Poissonized Plancherel measure, which is a Laplace functional that you see in the screen. We define a function q, which depends on t. T is the same parameter which we have used so far, and s is a number, is a real number. And we take the average over all of the possible partitions sampled with Poissonized Plancherel measure of the following product. This product is 1 plus e to the minus eta times this location of lambda I. This is nothing but the ith, minus the position of the ith particle in the Maya diagram, and then shifted by a certain number s. And as a function of s, it's the Laplace functionals. The Laplace functional as measures this average. Of course, and then we take the inverse of this function. So the question might be why is such an object interesting? Well, first of all, it's a Laplace functional of a measure, so is something completely natural to consider. But let me give some further explanation. So first of all, we can notice that such an object represents a natural generalization of the analysis of Logan and Shep, because if we take eta, this real parameter, positive parameter eta, to infinity, then we see that the function 1 plus e to the minus eta x, which figures inside this product, is converging to the indicator function, to the minus 1, is converging to the indicator function that our parameter x is positive. And therefore, when we take these parameters eta extremely large, the function qts basically reduces to the probability that lambda 1 is smaller than s. And so this gives you a complete, this reduces to the probability distribution of the first row, and therefore generalizes the result of Logan and Shep, but also generalizes the result by the famous result by Backteift and Johansen. This is not our point of view. Our point of view is actually that Laplace functionals of this type can actually be used and appear in the study of one-point marginals of solvable growth processes in the KBZ class. So I have some slides on this subject, but I decided to put them later. This is an application, and it is known that it is rather challenging to establish large deviation principles, and especially what are called usually lower tail large deviation principles for this object, and studying, having control over Laplace functionals of this type would be a step forward towards the study of these probabilistic systems. Another important part is that Laplace functionals of this type, these are functions of two variables, and one can prove that they are solutions, they are special types of solutions of integrable differential equations, which are essentially generalizations of the Korteweg-de Vries equation. In fact, it was found, there are several proofs around, but it was found that by my co-authors, by the co-authors, Kafas and Ruzza, that this equation, that this object Q satisfies a non-integrable equation called the cylindrical Toda chain. So the asymptotics analysis we find later to be related to other topics such as discrete orthogonal polynomials. I will comment on this later. And something that came well almost as a surprise is that considering these functions and especially its large T and S asymptotics, we discover new phase transitions which might be of independent interest. So this is a slide which should serve as a motivation, just to say we are not considering just any question. So maybe I can say before I state the main results, like if there are some questions at this point.
I have maybe two basic questions. One is when you introduce the probability on lambda, is this related to like the dimension of, so to each lambda you can assign an irreducible representation of Sn, and is this Plancherel measure related to that dimension?
Yes, this is precise. You spotted it, but exactly one could have I wrote this in the most simplified form, but one could have written this in the as saying that the probability associated to the partition lambda is proportional to the square of the dimension of the irreducible the reducible representation of the symmetric group associated to the partition lambda.
Okay, and it's the square because it's somehow how that appears in the regular representation, I guess. Okay, yeah, I got it. Thank you.
Yeah, there is the formula that says that if you take the sum of the square of the character, then you get the size of the group, and the size of the group in this case is n factorial.
Great, got it. Thank you. And sorry, the second question I had was you mentioned Zingerstan's work on lattice models and the Laplace functional. Can you yes?
So this work will be mentioned multiple times in the talk. So it is likely that your questions will be related because this work has been very influential.
Okay, great. Thank you. Yeah.
So let me state the result. So we have this Laplace functional. So the most natural thing to consider is for us is to consider its large its asymptotics for large arguments, and we find that this function q actually has an exponential decay and we are able to characterize precisely its rate function. So before the slide is about to fill up, but I presented here a plot of this rate function f. So the rate function f, let me explain the plot first, has essentially three regions. There is a region when the parameter x is to the right of 2. So remember that 2 is this number is a bit special for the Poissonized Plancherel measure because it's exactly the average, the law of large number of the first row. And so it is natural to expect that if we scale and since the parameter q is a generalization of the probability distribution of the first row of the partition, then it is natural to expect that if I consider x, if I calculate the probability that my partition is smaller than a number which is larger than its average, then this number should reduce to something trivial. And therefore, we find that, in fact, the function qt(xt) for x larger than 2 does not decay. In fact, it converges to 1, and its logarithm, in fact, is 0. So in this plot and in this formula, you see that the rate function is trivial when the argument x is larger than 2. But this is nothing unexpected. So there is another part of this plot, which is the blue part of the curve, which is, it's not as trivial as a constant 0, but is also rather simple. And in fact, is a parabola with a certain constant term, which is 1 minus e to the minus eta, where eta is the Laplace function, Laplace parameter, positive Laplace parameter appearing in the definition of Q, and and then a coefficient eta over 2 x squared. So this is a certain parabolic behavior which occurs when our parameter x is taken to the left of a certain critical value x star, which also is explicit, and its form is written here: -2 e to the -2 1 minus e to the 1 minus e to the minus eta divided by eta. So we see that this rate function has three potential phases, and the phase in the middle is something interpolating between a parabolic behavior and a constant, and its behavior will be given as follows. In fact, we find that the Poisson-Plancherel measure somehow the asymptotics of Poisson-Plancherel measure should be performed using using the theory of elliptic functions, and the region in the middle can be written rather compactly as this sort of deformation of the parabola that occurs for x less than this critical value, where we have a plus eta times an integral of a certain function L, and this function L can be expressed as a certain derivative of a rather simple function, which is written as a ratio of Jacobi elliptic theta functions. So these are, quite established function in mathematics, but I also remember their definition here. So of course there is some caveat. So you see that the right-hand side of these formulas does not so the left-hand side depends on x, but the right-hand side depends on a certain number k. But we have to specialize k, which is related to the parameter tau of the elliptic theta functions. This parameter k needs to be specialized as the unique, is defined implicitly as the unique solution in the range x star 2 of this equation. So this equation is basically can be solved by looking at this plot. So here I plot the function that takes k, a real number k, and plots two. Essentially, basically, we multiply and divide this by -2 over eta, so that in the right-hand side, all we are left with is x. So this is the plot as a function of k, and then we have to invert the value of this function. So it's clear that, from the plot is clear that this is a monotonic decreasing function, and as a result, in the region x star 2, in this case, x star is, in this case, eta is logarithm of 5, and x star is very, very close to -1, but it's not -1, it's like -0.99. Yes. And so this is inverting this relation. We recover x, we recover k as a function of x, and then we are able to compute this function, and also to plot to draw its plot. Okay, so this is the expression of the rate function, but of course this only gives you a rough idea of the behavior of the function. It gives you the first term in its decay, but one legitimate question is are there further order correction terms to this approximation? And the answer, in fact, is yes. And this is the content of this slide. So expansion up to constant order. We find that if you fix x smaller than 2, and you also fix this Laplace parameter eta, then if we pick x uniformly away from the critical parameter x star and 2, we have the following expansion, which holds uniformly. Let's analyze this function. So if x is smaller than this parameter x star, the rate function behaves as follows. So there exists a certain constant depending only on x, which in our work we do not characterize explicitly, but okay, it's a unknown constant. And then the function q actually behaves essentially as e to the minus t squared times the parabola, the rate function that we have seen in the previous slide. And there is no further correction term. So in a sense, the previous slide, up to the knowledge of this multiplicative constant in front, basically tells you exactly the behavior of the function q, of this Laplace functional of the Plancherel measure, Poisson exponential measure, in the region when x is less than x star. Recall that in this region, the rate function is actually exactly equal to a parabola. But as we have learned in the previous slide, so the interesting region, the interesting phase for x to make this function q very non-trivial is when is between the two critical values, x star and 2. And in this case, we find that this function q has a rich expansion. So we still have a certain multiplicative constant, c, which we do not determine. But then we see further interesting behaviors of this expansion. So first of all, there is another constant order term, which is oscillating, in fact, in t. So as we take t larger and larger, this function q at t, q of t xt, exhibits a certain oscillating behavior in the constant order correction. Then we have the decay is given by e to the minus t squared of f, just like proven, shown in the previous slide, where f is this elliptic perturbation of the parabola. And then we also find that there is no linear term in t, but there are logarithmic correction to this. These are okay. If we express exp of log as t, so this is an algebraic term, t to the a of eta. And these are all the diverging terms and constant order terms of this expansion. So for x in this pre-critical behavior, there is no oscillatory or logarithmic terms, and essentially this function here has exactly the behavior of e to the minus t squared times a parabola. On the other hand, in this critical phase, there are both oscillatory and logarithmic terms. And in fact, we also notice that the error size is different. And of course, maybe just from this slide, it might not be possible to find such a statement interesting. But in fact, the reason that the correction term in the lower in the second line is t to the minus 1/2 has to do with estimates coming from number theory. But okay, another interesting part of this expansion is that the logarithmic term is quite interesting to us, because usually in statistical mechanics, logarithmic terms of expansions of partition functions, they are related to, sometimes they are related to the topology of the system, which I will comment later, and other times are related to conformal field theory. So, but in our case, we actually do not know the origin of the true origin of this term, and I hope that in the future we will make this clear. Another interesting part of this, by the way, this function is explicit, and I did not report it because it's actually rather complicated, but is nice enough to be plotted. And here is a plot of this exponent, which, as you might notice, does not depend actually on x. So it's universal in x, but depends on this Laplace term, Laplace number eta. Let me also
I have a
comment.
question.
Yes, please.
Sorry for bothering. So how the function a behaves when eta goes to infinity?
So this is so this plot. So this function is actually rather complicated.
Oh, yeah, there is a plot. Sorry, I missed it.
Yeah, yes, but it's a legit. The true reason I put this plot here, and we also put the plot on the paper, is that okay, we have a rather difficult expression, but the expression is easy for a software, and it can be plotted. And from this plot, one might infer that the function diverges.
Yeah,
Um,
I see.
I will try to relate this divergence when eta goes to infinity to some behavior of to the proof of the main result, which I will present in the later slides.
Thank you.
So another thing that I want to mention is that I said that this function q actually solves solves a certain integral equation. And in the theory of integral equation, so it was actually pointed to us by some experts in integrable systems that the occurrence of such a implicit equation is actually not new, but it's actually it has a long history dating back to the some famous result by Gurevich and Pitayevsky, which solved the KdV equation in a certain oscillatory region. Oscillatory also relates to the fact that we have an oscillatory term here, but they found a solution of the KdV equation using also elliptic functions, but the elliptic parameter in that case was found through a physical relation, which is called the Wither modulation equation. So it seems that there is so this formula is actually extremely rich. So now I want to, unless there are some questions, maybe there are some questions. I would like to give some ideas of how to prove such a statement using only the ingredients presented in the previous slides.
Can I ask you a quick question?
Yeah.
So do you have like an explicit form of this Laplace functional Q? I mean, you have just it's like a solvable model. So maybe you have some kind of a formula for this, or
Yes, so this the function q, so this can be expressed in several ways. For example, the fact, it was proven by several people, I think by Borodin, Olshansky, and Okunkov, that the Poissonized Plancherel measure is a determinantal point process.
yeah, okay.
And as a result, this average can be expressed as a Fredholm determinant. So expressing this average as a Fredholm determinant is very useful because this is exactly what unlocks the asymptotics using a Riemann-Hilbert method. But actually, it is not the most useful things when it comes to establishing this type of asymptotics. So one can split the proof into two parts. One is to understand the rate function, and the other one is understanding further order terms. And the first one can be done in a almost elementary way, well, provided you have some good knowledge of elliptic functions. But the second comes from the application of the Riemann-Hilbert method.
So the relation between this one and the say trash rhythm distribution or KPZ just comes from the do you have the Fredholm determinant or something, or like it's not.
There are several ways to see this relation. One is that Tracy Widom is universal, for example, for log gases at the edge. So is a universal fluctuation seen at the edge of log gases. Okay, when the edge behaves like a square root singularity. So this is one possibility, but there are also different connections which do not involve this relation. I will see something I will say something later.
Okay. Thank you.
But of course, the result by Byteft and Johansson, which is written here, their famous result was where is the mouse? Yeah, their famous result was to actually establish Tracy Widom fluctuations, and in fact, the Tracy Widom fluctuations is related to the fact that this function here has cube C, I mean it attaches to 0 and it has a singularity of on the third derivative. So this is one way to connect the two results. But we will see the regularity of f in later slides.
Okay, thank you. Yeah.
Thank you. Okay, so I will. So my goal is to actually keep everything in a completely elementary description. So let's understand how to attack such a problem. So we have this function QTS. We just use the definition. This is an average of this function. We can open up the average and take a summation over all of the possible partitions. We have a probability measure, and we have the object which is being averaged over. The fact that the partitions, there are not too many partitions. There is a famous bound by Hardy and Ramanujan, which tells you that the number of partitions of size n grows like e to the some constant times the square root of n. And as a result, the number of partitions is much smaller than the weight, for example, e to the minus t squared. And therefore, we can approximate this summation. Okay, before I go there, we can approximate this summation with the maximum term. Okay? And when we approximate this summation with the maximum term, when t is extremely large, we can imagine that our partition becomes a continuous decreasing function from the y-axis to the x-axis, and our hook product becomes if we take the hook product, this is a product. If we take the logarithm of a product, it becomes a sum. And if we take a large sum, we can imagine that that's an integral. So the probability measure becomes essentially an integral, an exponential of an integral of this sort of L-shaped domain. So L-shaped, so the length of this L-shaped orange curve, integrating over the hypograph of this function phi, which is the scaling limit of our partition, and also the object that we are taking the average of is a product, but products we have already seen that they become exponential of sums, which is exponential of integrals. And if one quickly does some quick calculation, one understands that this term here becomes the integral of so it becomes the area contained between a line slanted of 45 degrees and attaching to well, not 45 degrees, eta, so the parameter eta divided by 2, but attaching to the point y on the y-axis and moving up and the lower part of this graph. So there is an intersection of the above part of the graph of this diagonal line and the hypograph of phi. So this v of phi y is nothing but the area of this yellow line, and therefore the maximizing this term becomes after we take the logarithm, becomes minimizing the hook product, the hook integral, which is the integral of this of the length of this orange segment, plus eta times this area. Okay, so when we take the infimum, we have to do some minimax. We have to take a shape that minimizes somehow the contribution of this blue line, but also minimizes the contribution of the hook integral. And in fact, this one can reformulate this sum and express this functional as a log gas. This was essentially done by Logan, Shep, and Darshik and Kerov in their analysis. But okay, one can reproduce the same argument to find that the maximizer of this of the term, the maximum term of this sum, can be approximated by minimizing a certain energy of a certain function f, which takes this form. So it is a double integral of f times this log correlation term, and then there is a potential term, and the potential is t log t minus t plus this eta. Sorry, it should not be eta q. It should be eta times this function t minus x. Now the function f relates to the partition, to the original partition as follows. So we already saw how to associate to a partition its empirical density, but the empirical density is not compactly supported. So we want to make such empirical density compactly supported, and so we basically half complement it by subtracting the indicator function of the negative real axis. And so the function f, I mean this term here becomes the maximum term of this sum, becomes in the large T limit e to the minus t squared times the minimizer of this logarithmic energy. Of course, doing all the calculations is a challenging task, but fortunately, this is a classical piece of mathematics. And now I'm ready to go to the next slide. So the question is, what does such a minimizer look like? Because eventually we want to completely describe this minimizer. Once we have the minimizer, we plug the minimizer inside this logarithmic energy, and we can finally compute the rate function, right? Because the rate function is nothing but the value of this logarithmic energy at its minimum over the set of function f, which can be obtained in this way from Young diagrams. So an original question for us is what does such a minimizer look like? And so what we did is just a numerical experiment. And here you see, the numerical experiment consists of a numerical minimization of such a functional. Here you will see that there is a diagonal line which attaches to the vertical axis at location x, and I will let x vary with you will see in the video. So at each timestamp, you will see exactly what the minimizer looks like as I take x in some values of x. So let's this is what we observed some time ago, and so we see that Sx. Let's observe this numerical simulation more in detail. as x is very large, well, this number here should I have not rescaled. Well, probably I should have rescaled. I should have rescaled this partition so that you would see that that this number here is exactly equal to 2t. So I guess that t in this example was taken to be like 45 because this number appears to be around 90, which is twice 45. But okay. So we take t large, so this number here, this is the first row. Compared to before, I also rotated the picture, so sorry about that. But okay, so this is approximately 2t, and when x is above 2t, we see that the partition doesn't change. The minimizer of this functional does not change unless x become less than 2. Now, when x enters inside the support of this original function, we see that the minimizer changes quite drastically. And in fact, if one really squints quite a lot, it would seem that the shape, the limit shape f, wants to do the following thing. It wants to have a smooth shape until a certain point near the intersection between the shape and this diagonal line. Then it wants to plateau slightly, and then it wants to go down in some smooth way. So the feature that I want to observe is the fact that around the intersection point between this slanted line and the profile, there we should expect a plateau. The reason is that this minimizer is trying to actually minimize the area put in this region. And as a result, it's trying to put as much area as possible to the other side of the partition. But this needs to be a partition, so it cannot be decreasing, going from the left to the right, from the right to the left. And as a result, we should expect the presence of a saturated region somewhere. And finally, we see that when we take x negative very large, the partition, so the partition essentially stops minimizing the contribution of the integral against the area contained in this region, and it just focuses on minimizing the remaining part of the integral, and as a result, the shape is just going to be a rescaling of the original shape. So you should see that the final shape is nothing but a rescaling of the original shape in the spatial and height direction. So this is a numerical test, but one can also imagine the situation in terms of the density. So we have an empirical density. We have x. This number here is around 2, where the support of the empirical density ends. And there is a number x. When x is larger than 2, then my limit shape does not change. When x enters the support of the famous Verschickerov-Logan-Shepp limit shape, then this minimizer develops a saturated region in the middle, and therefore the minimizer will be described by describing these two curved regions. So there will be a region to the left of this parameter x and a region to the right of this parameter x, and both they follow some non-trivial behavior. Now, if we take x smaller and smaller, at some point x is going to be too negative, and the limit shape will go back being a rescaling of the original Verschickerov-Logan-Shepp limit shape. So this qualitative behavior was proven earlier by myself, Das, and Liao, but in this paper we use softer methods, and therefore we were not able to actually understand when such phase transition occurs. But in this paper with Kafas and Ruzza, So we are able to do so. And let me just explain briefly how such analysis is done. So we already computed our functional, and okay. So here there is a mistake. Okay, here there is a mistake. So it should be the one below. But let's see. So we want to minimize this functional. So the natural thing to do is to take a variational derivative and impose that there exists at its minimum, which we call f star, this minimum. Each variational derivative is positive, and the Euler-Lagrange equation become equal to this. So the function f satisfying which minimizes this functional will have this property, which is it's a certain Cauchy transform of f needs to be equal to the logarithm of t plus this indicator function multiplied by eta halves. So there are lots of there are several more conditions. But which come by considering all of the possible choices of t. But one thing that I want to emphasize is that the previous analysis, and especially the previous numerical test, suggests that when x is between these two values, x star and 2, the equilibrium measure will have so this minimizer, which is in the jargon is called equilibrium measure, will be supported on two separated intervals. And this is why the title of this slide is two-cut case. These two separated intervals are called the cuts. So there is a way of rephrasing this Euler-Lagrange equation, of which you see only a small sample in this line, which is to use Plemelli formula and reformulate the task of finding f into a scalar Riemann-Hilbert problem, which is that of finding a certain function g, g prime in this case, g or its derivative, which is analytic in the complex plane minus two segments, and that satisfies a certain jump condition when the function g approaches these segments. In particular, we require that g g is going to be equal to there's going to be a relation between g and f after a subtraction of a logarithmic term. That's why you don't see such a logarithmic term in this condition, but up to such a simple fact. So our task is to find a function g analytic that satisfies a certain jump condition, and that also satisfies a certain asymptotic condition at certain points in the complex plane and at infinity. So this is where we got inspired by work by Zinjusten, which was mentioned before. Is that such problems might be quite difficult to solve. Well, there are actually books on how to solve such problems, but in every solution you are given the endpoints. So once you have the endpoints, you know how to write G prime. But in fact, yeah, so there is it is always a problem to actually reverse engineer the solution to actually use it to find the endpoints, and we know that the endpoints are useful to us because they represent they are useful to describe the equilibrium measure. But the key point is that we shouldn't look at we can look for a function g, but the smart thing to do is to not to look at g in the coordinate given by in the complex plane, but to actually consider a conformal transformation, which is this transformation here. This is if you remember, this is called a Schwarz-Christoffel map, which maps the upper half plane into a rectangle, and the rectangle we can normalize it so that so that's why there is a proportionality constant. We take the rectangle of height 2i pi and of width k, and the lower half plane would be mapped into another slice of another rectangle, and this in fact produces you a Riemann surface. But the point is that there is this conformal change of variables, and magically the function g prime can be completely understood in the variables offered in the W plane, on this Riemann surface. And in fact, on this Riemann surface, the function g prime of z of w can be analytically extended, and let me read, as the antiderivative of a periodic meromorphic functions with half periods given by this map and with two poles. And since we have the poles, and we have that this function is elliptic, then we can write it automatically using some results of complex analysis up to certain constants that we determine by the other conditions coming from the Euler-Lagrange equation. And this is the expression of the function g prime in the variables given in the parametrization of the Riemann surface. So zeta here is the Jacobi, is the elliptic zeta function. It's not the Riemann zeta function. So using this trick, then we can finally go back to the problem and reverse engineer the construction, the solution of this we can find the exact expression of the endpoints of our equilibrium measure, which now we call A, B, C, and D, depending on the value of x. And they are written in terms of the theta functions. Of course, I don't expect you to pay too much attention to all of these expressions, but there is a certain linear transformation which sends z to some multiple of z times z minus a shift. And these endpoints are explicitly written in this form, and here you see a plot. For example, the lower branch is the leftmost endpoint of our equilibrium measure. And in order not to leave you just with that formula, which potentially hard to digest, we have a way of parametrizing, and we can write explicitly the equilibrium measure, which we plotted earlier using this numerical test. Let's observe maybe this function again. So this the value, the orange region. So in this case, this orange, the rightmost point. So the leftmost point in this orange region is the value of x. So as I take x away, larger than 2, I have the arc cosine law presented in one of the first slides. Then when x enters the equilibrium measure, we see that there is the formation of a saturated region. And then when x becomes a large negative, the equilibrium measure comes back, being the certain shifted, a certain scaled arc cosine law. And we find a confirmation of these three phases. There is the phase where the limit shape is the arc cosine law. There is a phase in which we see the limit shape described by these elliptic functions, and then there is this other phase. And then this is how, in fact, this theorem is proven. But one can do actually much more. So once you have the equilibrium measure, then you can start extracting the higher order, the lower order correction terms, just like using the saddle point method. But as you know, Riemann-Hilbert is some sort of nonlinear variant of this saddle point method. But the logic is the same. The saddle point in this case is the equilibrium measure, and so given the saddle point, one can consider the full expansion. So now I want to just discuss a little bit. Okay, this paper is wrong, but this paper is already out on arXiv. But now it's important to understand the regularity of the rate function as common in statistical mechanics. And we find that in correspondence of the three phases, we find two phase transitions the transition from the phase where the rate function is constant to the phase where the rate function has this elliptic parametrization. And in this case, as I was asked before, so is there a relationship between the Tracy-Widom distribution and this problem? Yes, because for example, one relation could be that the rate function at around the value 2, which is the value of the average of the first row, has this singularity in the third derivative. So the first two derivatives of f are 0, both on the right and on the left branch, but the third branch, so the third derivative in the left branch is actually non-trivial, and it is equal to 1/12. And this number 1/12 is related to the lower tail of the Tracy-Widom distribution. Also, now, okay, so this takes care of this transition point. The other transition point, which is around -1, no, sorry, not -1, around this point x star, which in this case happens to be around -1, is actually of a different nature, is always a third order phase transition, but in this case, the third derivative doesn't even exist. And the second derivative has a singularity of logarithmic order. And in fact, at this point here, the second derivative is not even Holder, and it has this remainder. The third term is diverging. And this is in correspondence to the fact that there is a birth of a cut phenomenon. This is a topic in random matrix theory that I think was studied first by Claes in 2008. So sometimes, in this case, we have that this microscopic, region of lower density compared to this region of high density occurs far away from X. So if I keep moving X to the left, this part here shrinks but stays macroscopically spaced from X, and so we have a birth of a cut, but far away from the region where from X. So this is actually, I don't think this is such a phase transition was observed before in literature, because in this case we have so usually a birth of a cut is studied in continuous systems where there are no saturated regions, but in this case the birth of a cut is purely induced by the fact that the model is discrete, and yeah, so it could be interesting to investigate this more. But that's what we have so far. But I think I am basically out of time, and so maybe I will discuss only one application, but just very quickly. So let me decide what to describe. Okay, I will discuss this application. So I mentioned that there is the study of these functionals is related to characterizing the fluctuations of growth processes. So let me explain what growth processes we are talking about. So this is a deformation of the most famous polynuclear growth process, and here we have it. So in this case, we have to introduce a parameter q, which is related to the previous parameter as e to the minus eta. And we have a height function which evolves. Let me just show you a picture. We have a height function that evolves in this way. So islands can spread laterally, and they merge. And when they merge, sometimes they create a new island on top of them, and sometimes they don't. And they do. Let me do again. So here islands are spreading. So here they collide. Sometimes when they collide, they don't form any additional island, but sometimes they do. And the probability at which they form new islands is given by Q. And also there is also so the islands can also grow with a certain they can nucleate with an independent Poisson process of parameter T. So as you see, there is a so one can see a plot here. Maybe I'm gonna speed it up. So this is a growth process, which is exactly follows the description given before. I think in this case, Q is equal to 1/2, or I don't know. So so it is understood that the height function, the probability distribution of the height function, so for simplicity, one takes it at 0, after a certain independent random shift is exactly described by this function Q described so far. And this is a result of certain sort of algebraic manipulations or some bijective identity, some bijective proof. But okay, one can take this identity and using the fact that we already know the asymptotic analysis of the right hand side, we can extract the asymptotic analysis of the left hand side, and the result is the following. So the height function considered before satisfies a large deviation principle with the rate function phi given by a certain infimal deconvolution of the rate function f minus a parabola. So this parabolic shift comes from the fact that this identity holds, but on the left-hand side there is an additional shift, and the parameter and the function, the random variable s, in fact, is a Gaussian, and the Gaussian has parabolic tails, and therefore there is a parabola here. So here is a plot. So here is a plot of the function f minus a parabola, and you have to take the maximum, which is this crest here. But okay, so this is let me quickly finish. So we have studied this asymptotic the asymptotics of this multiplicative function, also of this famous probability measures, which is the Poissonized Plancherel measure. One application was presented, which is the large deviation of a model of growth. Another one, okay, I did not present, but one can also extract large deviations and phase transitions for a certain model of free fermions at positive temperature. That in that case, the temperature is actually the inverse of the parameter eta, the Laplace parameter. So there is also physical meaning behind this observable, but technically speaking, we give a description of a problem. We solve a Riemann-Hilbert problem where the equilibrium measure has two cuts. So in literature, there are several instances of such a thing, but the issue of having to also determine the endpoints is actually rarely addressed. And in fact, in literature, I only know one case essentially, which is the work by Zingersten, which is actually it's 25, 26 years old, but it keeps inspiring works, so it's a relevant paper. So as you can imagine, such analyses are also useful in other contexts. For example, currently we are working on extending this analysis to study the asymmetric simple exclusion process. So hopefully this the fact that we can manage such difficult situations can help us break new ground in these open problems. But a question that I have maybe for the audience, so I think about this question, but is what is the actual origin of the logarithmic term, right? So in the analysis of log gases, for example, in 2D log gases, the logarithmic term is related to the topology of the equilibrium measure. If there is a hole inside, so I had a discussion with Sung So Byun. You might know him. He's a professor at Seoul National University. So he actually suggested me that in 2D log gases, is an expert, but the logarithmic term is related to the topology. But in this case, we see that we don't know what the topology is, so maybe it's related to something else, which is actually to the criticality of the model. But we don't know what would be a relevant conformal field theory to insert into the study of this Plancherel measure. So I don't know. I will stop. I will stop here. So yeah, feel free to ask
Okay.
questions. Thanks a lot.
Okay, let's thank for the speaker for the wonderful talk. Okay, so is there any questions?
What do you mean by criticality of delta? So what is delta for the six vertex model?
So the six vertex. So in the work by Zinjusten, so he considered the asymptotic analysis of the partition function of the six vertex model with domain wall boundary conditions. So the six vertex model, the symmetric six vertex model, where there are only three parameters A, B, and C. One can define. So the physics of the system depends on a parameter delta, which is essentially given by a squared plus b squared minus c squared divided by 2ab. So this is I think you know this parameter. And so the physics of the system is completely determined by this parameter, which tells you if the six vertex model is describing a ferroelectric or antiferroelectric system, or in the case, so it is antiferroelectric when delta is less than -1. It is ferroelectric when delta is bigger than 1, and it is in a phase which is called disordered phase. So somehow this model cannot decide if to be a ferroelectric or not, or antiferroelectric is disordered. And in this region is given by the parameter delta between -1 and 1. It is conjectured that it is conjectured that in the liquid region. So maybe you know that the six vertex model with domain wall boundary conditions exhibits a limit shape phenomena. And the liquid region inside the limit shape should be described by a Gaussian free field. Whereas this is not true for the ferroelectric or antiferroelectric phase. About this, there is a recent paper by Dominique Copen where they established some similar result, but not for the domain wall boundary conditions. But okay, it is still conjectural to prove that the six vertex model converges in the liquid region to the domain wall to the Gaussian free field. But regardless, so this is what I mean by criticality. So the Gaussian free field is a conformal invariant object which appears when the model is critical. And the six vertex model is critical between, conjecturally between -1 and 1. And in that case, Zinjusten, and actually later Bleher and Lichty, found exactly that the partition function of the six vertex model has a logarithmic term correction in this region, which corresponds to the criticality of the model. So that's what I meant. But I don't know if this explanation holds in our case, because I don't know about any criticality. Well, I wouldn't know what.
I understand. Thank you. So, but when you said at some point that you're using some result in Zinjostan 2000, like a few slides prior, was that basically a complex analysis result, or was it more than that? So I'm not sure I understood very well.
So this is inspired. So Zinjostan had actually a slightly simpler system. So this is explained basically in this slide. So somehow Zinjostan had to minimize in order to solve his six vertex model asymptotics, had to minimize a function. Where is it? Had to minimize had to find a function g with a simpler jump condition, but nevertheless his solution was to cut. And in this case, considering such an elliptic change of variable, reduced the Euler-Lagrange equation for the endpoints into 4 linear equations. But in our case, we have slightly different situation. But nevertheless, the idea is that you have to change variables and look at the system with the coordinate given by the Riemann surface. So that's why inspired. Is okay. You can think of it as a complex analysis result. It's a fair description.
So I think what I'm asking is, you're not using a solvable lattice model result. You're using, right? So,
No.
so there's no at least in this lemma, there's no lattice model, or
No. This is a complex analysis. There is no
Okay.
lattice model. So, for example, in lattice model, sometimes we see the emergence of elliptic functions. Maybe the R matrix sometimes is written as elliptic solution, but I don't think those elliptic functions and these elliptic functions are related. I don't know. well, maybe deep down inside they are related, but
I see. Yeah.
in
Thank
this
you.
case, the elliptic functions are not related to any R matrix, any solvable model. They are related to the fact that if you look for complex for holomorphic functions on C minus a cut, then most likely you can change variable and put yourself on a Riemann surface, and that Riemann surface is going to be described by theta function. In this case, theta functions are of genus 1.
Okay, I understand. Thank you.
Thank you.
Okay, is there any other questions?
I
Okay,
have
so
a soft
oh,
question, which is, do you ever talk to Dominiel Cupin or people in his circle?
Do I have a?
Do you ever talk to people in like the people like Dominiel Cupin?
Yeah, I would like to. I mean, I spoke with several people. I don't want to name drop, but I actually did not explicitly ask this question because at that time this paper was not out yet, and so I did not want to speak without anything precise. But yeah, I would like to also probably understand their opinion on this result. In general, people with knowledge and expertise in conformal random geometry maybe might give some interesting opinion.
I see. So I think they have many papers. I don't know if himself or some of his collaborators regarding like the six vertex model. I don't remember now precisely what boundary conditions and in what situations. But I think they're somehow interested in limits of this model.
Yeah, I agree. For example, they usually consider, well, usually, I don't know, but it is simpler in general to consider the six vertex model on a torus, because in that case, the Bethe-Ansatz is slightly simpler. And then one takes the large torus limit so that you can establish some property of the six vertex model on the full plane. There was a recent paper, like 2 weeks ago, 1 week ago, where they actually proved criticality of the six vertex model on the plane, but for delta in some region, maybe -1 to -1/2, so something like this.
I see. Great. Thank you.
Thanks a lot for the question.
okay, is there any other questions? Okay, if not, let's thank the speaker for the wonderful talk today.